Hello, I'm back. This time, I'm going to cover another example of hierarchical clustering called a complete link style. Okay. So in that case, hierarchical clustering, we will have one more clip as well for the complete link type. So hopefully all these clips will help you. Okay, the first clip is single link, second clip is complete link. So let's refresh. What is single link and what is complete link? How is it different? So let's have to go look at the definition of variety of subtype of hierarchical clustering. All right, let's refresh. For example, given a data set of 8 data points, A, B, C, H, D, E, F, G right here, we'll see that by the definition of complete link hierarchical clustering, we are using the brown distance, which represents the maximum distance pair of two members between two clusters to represent how cluster on the left is far from cluster on the right. Okay, so complete link imply we are using the maximum distance, and we'll use this distance to update the distance metric during the stages of the complete link hierarchical clustering. So let's start with a similar data set. Okay, keep in mind, reminder, we are using maximum distance pair when update the distance metric. However, the algorithm is still going to pick the smallest one that appear on the distance metric no matter what. Okay, so this is the data of 6 data items. So in this example, the smallest one value is right here in the current distance metric. So that means we can create. So if I call this step 1, this produces the output of A and C merged together. And at the same time, we get to update this distance matrix. So let's look how it updates. So now I can draw A and C together. The rest are B, D, E, F. Again, this I'm update to A and C, B, D, E, F. Again, distance metric for any diagonal cell, the update will be just remaining 0 because it means distance to itself. Now for the row that doesn't have anything to do with A and C, okay, so these will be affected. Okay, will be copy. So if you have nothing to do with A and C, we will copy. Okay, so in that case, the copy one, the BD we can copy is 3. (10), 16, and DEF will be 20 and 11. E and F I can copy as 18, but the top 4 cell I will have to update. For example, this cell is from the maximum of 2 value, which is AB, which was 5, and CB or BC, which is 6. So the update value of the maximum of the 2 was 6. And we will do the same to the maximum of the next cell. So the final update come out like that. You can pause the video and see if you can come up with the same. If not, model me. Let me know. So after this step 1 result, we are proceeding to step 2. Okay, so that's step 2. So while step 2, the position that we will perform the merging is still at the smallest value in the distance matrix. So that means we're going to merge B and D. So that implies that now distance matrix will be A, C, B, D. Notice the vertical height that's taller because we have more members merged later state. The more you merge later, the height is higher. The height will be higher if you merge at the later state. In this case, BD is taller vertically. And we also have to update the distance matrix as well. So with that, the distance matrix for the next step, which is the step 3, will consist of A, C, and BD together. Okay. And E and F by itself. So now the distance matrix will be updated one more time, but just like what we had done before. Okay, again, diagonal is 0 because it implies the distance to its own self, but the column that we have to update are row and column that has something to do with B and D. So in this case, A, C to E can be copied right away, which is 15. And A, C, and F can be copied because it has nothing to do with B and D. That's 14. And E and F also can be copied right away because it has nothing to do with E and F. But the rest 3 cells we have to calculate the update. So for example, this cell is the maximum of AB, AD, CB or BC, and DC or CD. Okay, which one? So if we locate the previous distance matrix, we can see that the AB was 5, AD was 7, so 7 is bigger, BC was 6, so far 7 is the highest. Let's look at CD. CD was 12, so the number that we will update was 12. Same thing for the cell here, BD and E. Okay, BE was 10, BE was 10, and DE was 20. So the update value is 20. Same thing to the BD and F. BF was 16 and DF was 11, so 16 is update there. So even with the update distance metric, the 12 was the smallest, so that create the next output dendrogram that BDAC will be merging together. So you got AC, you got BD merge later, and the whole two bunch merge together. And if we update distance metric, so now we'll have A, C, B, D together and E, F. So same thing. So we have A, C, B, D, E, and F. Okay, diagonal distance becomes 0. Now for E and F, nothing changed, so we can copy the value of 18 there. But for this cell, it's the maximum of AE, CE, BE, and DE. So in that case, AE was 15, BE was 10, CE was 8, but DE is 20. So that should be updated to 20. And similar update lead the F to 16. Okay, so that means the next step, the merging, is looking at smallest value here, which is 16. So this is the step 4. So that means in step 4, what we get was that AC merge, and then BD merge with AC, and the whole bigger set merge with F. That means the next step, step 5, we would have a set of A, B, C, D, F together and E by itself. Again, diagonal 0, and if we update that cell, will come out as 20, which is the maximum of AE, BE, CE, DE, and F. So in this case, that is the only way to merge was at this last sequence, which is the whole big set merge with E. So that means at the end, what we got is AC, then we merge BD later, then these two merge together, and then merge with F until the final round merge with E. So this is the final dendrogram of complete link hierarchical clustering. Alright, hope you run through this again, and let's see if you have any question, or if I make any error, let me know. Thank you.